Hello everyone, my name is Dr. Redwan Alqasemi. I'm a mechanical engineering professor at the University of South Florida. And today I'm going to talk to you about manipulator kinematics. And this chapter talks about forward kinematics for robotic manipulators. As a summary for this chapter, we're going to be learning about how to find the Cartesian pose or orientation and position in space for the end effector if we are given the joint angles for the robot. So if we have each joint angle of our robotic manipulator, where would the end effector or the gripper be in 3D space? Let me talk a little bit about the learning objectives here. The first objective is we're going to be learning about different types of joints that we use for manipulators and the parameters that are associated with these types. So we're going to talk about two of these types, which are revolute joints and prismatic joints. Then we're going to learn about how to assign link frames for each one of these links. And then we're going to assign these XYZ frames into each link from the ground frame all the way up to the gripper. And then we're going to see how we can extract the DH parameters from these frames. These DH parameters are the same as the 4 parameters that we have for joints and links that we're going to talk about later on. And then the third objective is to solve forward kinematics problems. So basically find the end effector transformation matrix if we are given the joint angles for each one of the joints. Let me start here by introducing what kinematics means. Kinematics is the science of object motion that looks at the motion of objects without regards to what are the forces that are causing these motions. So basically you can think about it as the position, velocity, and acceleration of objects, and you are not looking at what are the forces or moments that cause this motion. If we look now at forward kinematics, it's a method that we can find the end effectors or the grippers position and orientation in space at any given joint values of the robot. So if the robot has whatever specific joints, once we give them joint values, then where would be the end effector in 3D space? The third thing I want to talk about here is the robot manipulators. We usually look at this as a system of bodies that include links and joints. And these links are rigid bodies, and they are connected by these joints that can be of any kind. And we'll see what are the kinds that we're going to cover in this course. For this course now, we're going to consider only two types of joints that we're going to look at and look at the kinematics that are involved with these joints. And these two joints are revolute joints and prismatic joints. So revolute joints are considered in this application a single axis rotational joint. Okay, so we're not going to look at multi-axis rotational joints. We're going to look at only single axis rotational joints. And these are connecting two rigid bodies or two rigid links together. As we can see here, if we have rigid body 1 and rigid body 2, we call them links. They're connected with a revolute joint that rotates about a single axis. So we call this revolute joint, and the joint value would be theta. The second kind of joints that we're going to consider for this course is the prismatic joint. And it's a single axis translational joint that connects two rigid bodies together. Again, so this one here is a single axis of translation. We don't consider multiple axes of translation. If you look at this figure here, you can see that the variable for this kind of joint is called d. So that's the distance of how much this joint moves link 1 from link 2. Now let's see how we can describe link and joint pairs. So for link and joint pairs, they can be described using 4 parameters. Out of the 4 parameters, 2 of them describe the link and the other 2 describe the joints. Okay, so for each pair, we will have 4 parameters. 2 of them will be for link and the other 2 will be for joints. Now, remember, I want to emphasize here on something that, out of the 4 parameters, 3 of them will be constants, and 1 of them will be a variable. That variable will be the joint value, okay? And we're going to see what are the 3 constants and what's the 1 variable parameter that will be the joint value once we go through this. Now let's start with the link description. A robotic manipulator can contain 2 or more links, and these links are described using 2 parameters. So if we look at this, we always start with the ground as link 0. It's part of the chain of links. So we always call it link 0. And then we move on to link 1 and link 2 and so forth all the way until we reach the last link, which is link n in this case. All right. And each two of these links is connected with a joint, either prismatic joint or revolute joint for our course. All right. So this chain of links makes up the manipulator, and we start with link 0, and we go down to the last link. In this case, I called it n. So each link will be described using 2 parameters. Remember, we have here 4 parameters total for link joints pairs. 2 of these parameters are for links. So for the link, we'll have 2 parameters that we're going to describe or define right here. The first parameter is called the link length, or AI-1. And I-1 is just an index that indicates which A we are describing. This is for link I-1. So if we're describing the link length for link I-1, we call it AI-1. All right. And the definition of this link length is the length along the common perpendicular line between joint axes. So if we look at link I-1, and we have joint axis I-1 on one side and joint axis I on the other side, okay? Between these 2 axes, there will be a common perpendicular, a line that would be perpendicular to both axis I-1 and axis I, okay? That common perpendicular would make a length between these 2 axes that we would call link length, okay? So that link length AI-1 will be the distance from axis I-1 to axis I along the common perpendicular line between these 2 axes. In this figure that you look at here, we have axis I-1 and axis I, both of them are parallel. If they're parallel, that means there are infinitely many lines between these 2 axes that would be perpendicular to both of the axes. So any line from here to here, including that red line that you see, as long as it's perpendicular to both of axis I and I-1, the length of that line would be my link length. Okay. The second parameter is called the twist angle, or alpha. And again, the index I-1 indicates that this alpha is describing the parameter for link I-1 that you see here. And the definition of the twist angle is the angle about the common perpendicular line between joint axes. So if we look at this figure is similar to this, except that we twisted one end of the link. And again, this is like think about it as rigid twisting. So you have to put this on a machine and twist it. So if we look at this joint of axis I-1, it's going up and down, and the joint for axis I is actually going this way, which you can think of as going into the screen or out of the screen. Okay, and there's a twist between this axis and this axis. So if we take this axis of I and just shift it into here so that we can see the angle, so this axis right here is actually axis for I. Okay, now we can clearly see that angle right here that you see in red. Okay, and that angle is basically the angle between axis I-1 and axis I about the common perpendicular. Okay, so since axis I-1 and axis I are not parallel, there will be a unique line, a single line, that would be connecting these 2 axes and be perpendicular to both of these axes. And that line would be right in here where these intersect. So if you can see the intersection point, this line represents the axis I here, and this line represents axis I-1 here. So that intersection point, if you draw a line from here to here, that would be a unique line that will be perpendicular to both axis I minus 1 and I. Okay, and the angle between axis I minus 1 and I about that common perpendicular would be our twist angle for this particular link. Okay, now I want you to understand that both of these parameters, the link length and the twist angle, are constants. So out of the 4 parameters, we said 3 of them are constants and 1 is variable. So the 2 that we describe the link with are both constants always. Okay, so A is always constant and alpha is always constant. And both of these describe the link. Now, these 2 parameters are for each link separately, so we have to describe 2 parameters for link 1, 2 parameters for link 2, and so on. Okay? Now let's take an example about link description. How do we describe the link, the 2 parameters that we talked about? So this example asks you to find the link length A and the twist angle alpha for the shown link that supports 2 revolute joints. So these are 3 different orthogonal views of the link and joint pairs. So we have a bearing here. As you can see, there's the shaft that goes in here. And there's another bearing here where the shaft goes. And you can notice that this block for bearing B and the block for bearing A, they are not parallel to each other. They are at a twist. Okay, and you can see it from this view. The twist about 45 degrees here. Okay, and then you have some lengths here. So this block here is 2 inches, and then from here to here is 5, and then this block is 2 inches. And we need to find the link length and the twist angle. So let's start with the link length A, and we have to always consider this from the center of the bearing, which is this point right here. Okay, so that would be half of the 2 inches, which gives me 1. So I have 1 inch from here to here, and then I have this whole length, which is 5, so that makes 6 inches so far. And then again, I have to go to the center of the second bearing, which would be 1 out of the 2 inches here. So that would give me another inch in this distance here. Okay, so that gives me 1 from here to here, plus 5, that makes 6, and then plus 1, that makes 7. Okay, so if we look at the answer here, link length, half of 2, which is half of this 2, plus 5, which is this length here, plus half of the other 2, which is half of this 2. Okay, and that would give me 7 inches for the link length. Now for the twist angle, you can clearly see it from here. The first bearing has an axis going up and down this way, or in this figure this way. And then the second link has an axis that goes actually 45 degrees, as you can see this way here. Okay, so the common perpendicular would be somewhere right in the middle where the dot is here, and the angle between axis bearing A and axis bearing B about this dot right here, which is the common perpendicular between these 2 axes, would be 45 degrees, which is the angle from here to here. Okay, from here to here. All right, so that twist angle alpha would be 45 degrees. After describing the link with its 2 parameters, now let's move on to describing the joints with its 2 parameters. Okay, so now we're going to go to joint description. We already described the links. Now we're going to describe the joints. A robotic manipulator can contain 1 or more joints. Okay, and joints are described using 2 parameters. Remember, for the links, a minimum of 2 links are required for a manipulator. As for joints, a minimum of 1 joint is required for a manipulator. Right? So if you look at this graph here, we can see that we have a manipulator here in general that has joint 1 that connects the link of the ground to the first link, and then joint 2, and then joint 3, and so on up to joint N. That would be the last joint in our manipulator. Okay, and to describe each one of these joints, we will have 2 parameters to describe them. Okay, so we already described 2 parameters for links, and here we're going to describe and talk about the 2 parameters for the joints. Now, the first parameter for the joint is called joint offset, or D, and the I here is an index that indicates which joint axis you're describing, which joint. So in this case, we're describing joint I for axis I. Okay, and the definition of joint offset is the length along the axis of motion between two common perpendicular lines. Okay, so let's look at this here. We have axis I, which is the joint that we're describing right now. Okay, and we have a link before, link I minus 1, and we have a link after, which is link I. Okay, this link will have a common perpendicular that you see this green line, which is from this axis I to axis I minus 1, somewhere here. And then here we have another common perpendicular line, which was between axis I and axis I plus 1, which would be somewhere here. Okay? So if we look at this common perpendicular first and the other common perpendicular, the distance between these two common perpendicular is called the offset for this particular joint. Okay? So for joint I, axis I, the joint offset, or D, would be the distance between this common perpendicular and this common perpendicular that would be describing the links. Okay, so from description of the links we can also find that D offset that describes the joint. So that is the first parameter that we have or we use to describe the joint. The second parameter is called the joint angle, or theta. And again, the I here is an index that indicates which axis we're talking about, or which joint. So for axis I, or joint I, we're using theta I. And definition of joint angle is the angle about the axis of motion between two common perpendicular lines. So again, if we look at this here, let's say we have axis I, this is the joint that we're describing. The joint before axis I, which is here, axis I minus 1. Now this axis I minus 1 and axis I have a common perpendicular line, which is this line. Okay, and then if we look at axis I plus 1 right here, and there's a common perpendicular between axis I plus 1 and axis I, which is this dot, and that common perpendicular would be this line. Okay, so this is one common perpendicular, and this is another common perpendicular. And the joint angle is the angle between these two common perpendicular, this one and this one. So this is our joint. So as this joint moves, the common perpendicular line here and the common perpendicular line here will start moving as well. So the angle between them will be changing as well if it's a revolute joint. Okay, so this would be the angle. This is the first common perpendicular and the second common perpendicular, and this is joint angle theta I. Okay, so that would make two joint parameters. And we already described the link parameters, the two link parameters. That makes a total of 4 parameters. Remember we said that out of the 4 parameters, 3 of them are constants and 1 of them is a variable. And we already learned that the parameters for links are always constants. That means one of these will have to be constant and one of them will have to be a variable. Now, I put here some note that for revolute joints, theta is the variable and D is the constant. Okay, so whenever we have a revolute joint, it makes sense. The revolute joint will have a variable that's changing, which is the joint angle theta, and in that case D would be constant. And then for prismatic joints, D is actually a variable, since the prismatic joint has motion in linear motion, and then the angle theta would be a constant. Okay, so for prismatic joints, D is variable and theta is constant, and for revolute joint, theta is variable and D is constant. So if we look at a pair of link joint together, again, these two parameters for joints, they are repeated again for each one of the joints. So you have 2 parameters for joint 1, and then another 2 for joint 2, and so forth all the way to the end. So if you look at a pair of link and joint parameters together, 4 parameters, out of the 4, we'll have 3 constants and 1 variable. Okay, and that one variable could be either theta if the joint is revolute joint, and will be d if the joint is a prismatic joint. I want to introduce here Dennevit-Hartenberg parameters, or we call them DH parameters for short. And these are the parameters that we just introduced for joint and link pairs. Okay, so the DH parameters are basically the 4 parameters that we defined for the link joint pairs. And these are A, I minus 1, alpha I minus 1, DI, and theta I. Now, if you look at this, this is like a general awkward kind of looking link, okay? Just so that we can put things in 3D perspectives. So if this is joint for axis I minus 1, okay, and this is the joint for axis I, okay, and they are twisted and, you know, at a distance, and this is here link I minus 1 between these two joints, okay. Now, if we take axis I minus 1 and axis I and we try to find a common perpendicular, there will be at least one unique line, at least one, that would be perpendicular to both axis I and axis I minus 1. So let's assume that this line is right here. So as you can see, this is perpendicular to this and perpendicular to this as well. Okay, so AI minus 1 would be the length of this common perpendicular line. All right, and then if I take this axis I minus 1 and axis I, okay, and just take one, just shift it along the common perpendicular line. So basically this line is the same as this, and then measure the angle between axis I minus 1 and axis I. Okay, that angle here will be the twist angle, alpha I minus 1, that we see right here. Okay, and then if I look at this common perpendicular that has AI minus 1, and then the next common perpendicular, which is right here. So I don't have, you know, axis I plus 1 drawn here, but let's assume that this is the axis for, or the common perpendicular for between axis I and I plus 1. So let's call this AI, for example. Okay, now the distance between this common perpendicular line that has AI minus 1 and this common perpendicular line that has AI, that distance along this axis I would be DI. Okay, so that would be a joint parameter, DI. All right. And then finally, if we look at this common perpendicular right here, okay, and if we look at this line that extends the common perpendicular for AI minus 1, okay, these two lines, okay, and then we look at the angle between them. So the angle between this line, the first common perpendicular, and this line, the second common perpendicular, that angle will be theta I, which is the joint angle that we have. Okay, so this basically shows you all the 4 parameters in one plot, and you can just see how you can extract this. And again, this is a very general drawing, but for each example it will be probably simpler than this to figure out what these parameters are. Okay, as we talked about earlier, one of the 4 parameters is a variable. Out of all 4 of them, one of them is variable. And when we talk about revolute joints, theta would be variable, and A, alpha, and D would be constants. And if we're dealing with a prismatic joint, then D would be variable, and then A, alpha, and theta will be constants. Okay. Now, I want to add this here just to, to tell you about some convenience ways to reduce calculations later on down the road. It's always good to design once we attach our frames that we're going to see later on in later slides. It's a good idea to set our A0 and AN and alpha 0 and alpha n to zeros. Okay, so A0 basically is the link constant for, or link description constant for link 0, the ground. and an is that link description constant for the last in the effector, okay? And then alpha 0 is the twist angle for the ground, and alpha n is the twist angle for the last, the end effector, which is at the very end of my robotic chain, okay? And we're going to see how, if we set these to 0, how we're going to reduce our calculations down the road. Also, for revolute joints, it's always a good idea to set D1 to 0 for revolute joints. And for prismatic joints, it's also good to set theta 1 to 0. Okay? And when I talk about setting it to 0, it doesn't mean that you just assume it's 0. No, but when you do the attachment of frames on each link, you have to attach it such that these values would go to 0. And we're going to see how we can do such a thing.